All right, let's talk about something we all deal with, the electricity bill. Have you ever looked at that thing and just wondered what you're actually paying for? Well, today we're going to demystify the power flowing through your walls and break down the science behind AC electricity and those monthly charges. So let's kick things off with a little mystery you've probably noticed right in your own home. You know your phone charger, that little block? Ever unplugged your phone but left the charger in the wall and then noticed it's still a little warm to the touch? Yeah, what's up with that? It's clearly using power, but for what?
Well, there is actually a name for this. It's called vampire power. Kind of spooky, right? It's that phantom energy that gets sucked up by devices even when they're supposedly off. And to really get how this happens, we've got to dig into how AC power actually works.
Okay, so let's dive right in. We're going to start with the kind of power that's easiest to wrap our heads around, the power that actually does stuff. This is what engineers call real power, and you'll usually see it represented by the letter P. Now, if you dig into the technical side of things, like in steady-state AC power calculations, you'll see this defined as the energy that gets transformed to do something tangible, like creating heat or light. Think of real power as the absolute workhorse of electricity. Seriously, it's what's making your light bulb glow, what's toasting your bread, what's spinning the blades in your blender. It's the useful, productive energy that gets work done. And we measure it in a unit we all know and love, the watt. Now here's the really crucial part, the reason this matters to you. Real power is what the utility company is tracking. It's what they bill you for. So when you see kilowatt hours on your statement, that's just a measure of the real power you've used over time. Plain and simple, this is the power that costs you money. But, and this is a big but, in AC circuits, that is not the whole story, not by a long shot. Real power has this kind of hidden partner, a player that's absolutely essential for a lot of our devices, but it doesn't actually do any work itself. So let's meet reactive power, or Q. The best way to picture this is to think of energy that's just sloshing back and forth. It's constantly being exchanged between the power source and these little components inside your electronics, things like conductors and capacitors. Their job is to store energy. So this reactive power is crucial for creating those magnetic and electric fields that make devices work. But here's the weird part. It doesn't get used up. It just gets borrowed and returned, over and over again. So here's the main difference, laid out nice and simple. Real power, measured in watts, is the energy you actually consume. It's gone, used up, turned into something else. But reactive power, which has its own unit called volt-ampere reactive, or VAR for short, that's the energy you just borrow. It's needed to keep the energy fields in the circuit going, but it gets sent right back to the source with every single cycle. All right, so we've got the working power, and we've got the borrowed power. To really see the full picture of what's happening inside a circuit, we need to put these two together. And that brings us to something called complex power, represented by the letter S. Just think of it as the total power that's flowing from the grid to your device. It's the grand total combining both the real power that's doing the work and the reactive power that's just sustaining the fields. It tells the power company the full energy load they need to be ready to supply. Okay, so let's do a quick recap here. We've got P, which is real power. It's in watts, and it does the actual work. Then you've got Q, reactive power. It's in VARs, and it's just exchanged, not consumed. And finally, S, the complex power. That's in voltamps, and it's the total power in the circuit. Got it? Good. Okay, now that we have a handle on real, reactive, and complex power, we have all the clues we need. We can finally solve the puzzle we started with, the mystery of that warm idle charger. So here's exactly what's going on inside that little block. Your charger has something called a transformer in it. Now, just by being plugged in, that transformer needs to borrow reactive power, the Q we talked about, to keep its magnetic field going. But here's the catch. That whole process of borrowing and returning energy, it's not perfectly efficient. A little bit of that energy gets lost as heat. And that heat loss, that is a tiny amount of real power being consumed. And since your utility meter only measures and bills you for real power, bingo, that's what shows up on your bill. That, my friends, is vampire power. So understanding this difference kind of changes how you look at your gadgets, right? It's not just about whether something is on or off. There's this hidden work happening inside our electronics all the time. And that leads to a final thought for you. Now that you know the science behind it, what other power vampires do you think are lurking in your home? Your TV, your game console, maybe even the clock on your microwave. The list is probably longer than you think.